Hi class, let's do some linear algebra. Recently we've been talking about linear independence of vectors. One thing that we want to realize is that sometimes linear independence is easier to visualize than in other times. So sometimes linear independence is easy to visualize. So for example, if I had a few vectors, let's say I've got the vector v is equal to 2, 1, w is equal to 3, 4, and u is equal to -1, -1/2. We want to put them on these axes that I've drawn. One thing that you'll realize is that here's v, here's u, and here is, here's w, and here is u. And while my drawings are not entirely to scale, you can start asking yourself a few questions. So are v, w, and u linearly independent? In two-dimensional Euclidean vector space? And you'll notice, just by eyeballing it, that u and v are not linearly independent. Together they lie on the same line. So v, w, and u are not linearly independent because v and u are linearly dependent. But v and w together do not fall on the same line, so they are linearly independent. This is very, very easy to visualize. Sometimes linear independence is not easy to visualize or to understand visually. So for example, if I set up my axes again, I can think about these two, definitely not to scale, but e to the x and e to the -x. Okay, what does it mean to say whether these two are linearly independent? They definitely seem related to each other, but does this correspond to linear independence or linear dependence based on the definition that we have before? So let's say we've got an f of x, which is a function instead of just a vector in Euclidean space, and say they're functions in the vector space, continuous functions from -∞ to infinity. They are linearly independent if f of x plus g of x equals 0 with some coefficients c1 and c2, then this implies that c1 and c2 have to be 0. Since we are doing functions instead of just vectors, it might be easier to think about what this 0 actually means. This 0 is the function. It is the 0 vector in this vector space. It is the function that sends everything to 0. So I'm going to just add a triple line here to indicate that it's the function that is uniformly 0. It sends everything to 0, or it's always 0. Okay. Having said that, we have to also realize one additional subtlety before we dive in, that f of x, and g of x vary depending on x. So this has to be true for all x. This is what linear independence looks like for functions as opposed to vectors in Euclidean space. Let me introduce the tool that is going to help you with this. Let's talk about the WRONSKIAN. Okay, if f1 through fn are in Cn minus 1 from a to b, remember this is the functions on the interval a to b that are real valued, as in the output is a real number, they are continuous, and they have n minus first or n minus 1th derivatives. You can take a derivative and then a derivative of that and then a derivative of that up to the n minus 1. And recall that in this vector space, the zero vector, as I was saying before, is the function that sends everything to 0. So for all real numbers in the interval a to b x, f of x is going to be 0 every single time. Given that some expression that's going to help us figure out if these are linearly dependent or linearly independent, we're going to have to explore these functions with coefficients and ask ourselves, is this 0? Of course, the CI are reals. Here's the trick. We're going to take derivatives. Okay, so we're going to start with what we have. And we're going to take the first derivative. Remember, taking derivatives is linear, so you can pull out the coefficient ci, and it distributes across the plus. So if I take the first derivative of both sides of this equation, I'm going to get c1 times the first derivative of this first function, all the way down to cn times the first derivative of this last function. And on the right-hand side of the equal sign, we're still going to get 0. We're going to keep taking derivatives until we get c1 times the n minus first derivative of the first function, all the way down to cn. Okay. Look at this closely. It should remind you of things that we've done before in the following sense. We can express this system of equations via matrix multiplication. Said otherwise, we've got f1x all the way over to fnx, f1 first derivative, all the way over to fn first derivative, all the way down to fn minus 1 x, fn minus 1 x, considered as a matrix, times the vector c1 through cn, where the ci's are real numbers, should be equal to the 0 vector, as in this sense, the function that is uniformly 0. Definition. If f1 through fn, as we've been talking about, are in c to the n minus 1, ab, the WRONSKIAN is a derivative denoted w, square brackets with the functions in here, evaluated x. This is defined to be the derivative of the matrix above. I'm going to call, well, this is the WRONSKIAN, right? And if this in here is an f is F, which is an n by n matrix. This is just the determinant of the matrix F. If the WRONSKIAN is not uniformly zero, as in there is some x for which this determinant is not zero, then the F1 through Fn are linearly independent. Let's do some examples. Example. Calculate the WRONSKIAN of these two. What can we say, given whatever this WRONSKIAN is, what can we say about the linear independence of Ex and e to the minus x in the vector space? Continuous real value functions that are continuous in the whole real line. Well, let's do it. E to the x, e to the negative x, as a function of x, this is going to be, well, we're going to take the determinant of a matrix. Here are our original. Then in the second line, we're going to have the first derivative of each. So we're going to have e to the x and negative e to the negative x. This, by finding the determinant, is e to the x times negative e to the negative x minus e to the x times e to the negative x. This is negative 1 plus negative 1 times 1. This is negative 2. So the WRONSKIAN is negative 2, the function that sends everything to negative 2. And we'll notice that it is not uniformly 0 because it's negative 2. So Ex and e to the negative x are linearly independent in this vector space. Let's do another example. Example, how about cosine of t and sine of t? Well, the WRONSKIAN of these two functions as functions of t, it's going to be the determinant of a matrix. On the first line, we have the originals. On the second line, we've got the first derivative, negative sine t. Then the first derivative of cosine t, so of sine t is cosine t. We do just enough derivatives so that we have a 2 by 2 matrix or an n by n matrix. In this case, now we can find the determinant. This is going to be cosine squared t plus minus sine squared t, which is equal to cosine squared t plus sine squared t. And if you'll remember your identities, this is equal to 1, which is certainly not uniformly 0. So this means that cosine t and sine t are linearly independent, even though, obviously, if you were to sketch them, they would look very much related. Okay. Question. In everything that we've been doing before, the determinant is supposed to tell you if and only if a few vectors are linearly independent. So if the determinant of the matrix made up of the vectors is 0, then those vectors are linearly dependent. If the determinant is not 0, then those vectors are linearly independent. This was in Euclidean vector space. However, all I've told you is one direction. I've told you that if the WRONSKIAN, this determinant of this special matrix, is not 0, then the functions are linearly independent. So a question that you might have is, if the WRONSKIAN is uniformly zero, can we say that f1 through fn are linearly dependent? No, unfortunately. And here I'll walk through a classic example that's given by the two functions x squared and x times the absolute value of x in c -1 to 1, so the continuous functions on this interval. Okay, if we want to figure out if these two things are linearly independent, we set up our equation. And we try and figure out what C1 and C2 have to be. I'll tell you a little bit that we can take a shortcut, and we'll consider it for two values. First, for x is equal to 1. Well, if we plug that into this equation, we get C1 plus C2 is equal to 0. We can next consider it when x is equal to -1. Plug that in, we get C1 minus C2 is equal to 0. So this only solution is C1, C2 is equal to 0, 0. C1 is equal to 0, C2 is equal to 0. And this gives us that x squared and x times the absolute value are linearly independent. Just going back to the definition. However, let's look at the WRONSKIAN as a function of x. Well, on the first line, we're going to have x squared and then x, absolute value of x. Then on the second line, we have the derivatives. And if you think a little bit about this, you'll see that this is what we get. Finding the determinant, we've got 2x, absolute value of x times x squared minus 2x times absolute value of x. This is uniformly 0 for all x. You might have a little bit of trouble imagining why this might be so. So I'm just going to give you a little bit of an idea. This is what it might look like. And I'll tell you what happens to this WRONSKIAN at x is equal to -2. We've got 4, -4, -4, 4. And we'll notice that this, if we multiply by 1, 1, we're going to get the 0 vector. How about, but at x is equal to 2, the WRONSKIAN is going to be 4, 4, 4, 4. And we'd have to multiply by 1, -1 to get 0, 0. All of this is to say is that there is always a solution to this equation of matrices. However, the solution is discontinuous. It flips when you change from x is equal to positive to x is equal to negative. So there's not one vector that solves the whole thing, which is why our two functions are linearly independent. So this is all just an idea down here. All right. Let's do an exercise. Here's an exercise for you. Recall the vector space Pn of polynomials of degree less than n. Are the functions 1, x, x squared, all the way up to xn for some n, are they linearly independent in this vector space? course, I want you to use the WRONSKIAN. That being said, we've learned how to use the WRONSKIAN. You might still have some lingering questions. Number one, why do we care so much about linear independence? That we're going to get to soon. Number two, as we've hinted at in previous lessons, does linear independence of vectors, say column vectors in a matrix, tell us something about the column space of that matrix? Let's call it matrix A, the row space of that matrix, and the null space of that matrix as vector spaces. Think on this. Talk to you next time.